Hello everyone, and welcome back for the third part of this OpenTelemac flooding simulation tutorial. In the last part, we created the following files: GeoEvet, which is the geometry and the mesh containing all of the physical fields, the createBoundary file, which contains the data at the boundaries. Today, we're going to create the steering file .cas, where all of the instructions to give to OpenTelemac are going to be. This .cas file is simply a text file that you can edit with your favorite text editor. In my case, I'm going to use VS Code. And we're going to start with this template, which is an empty steering file. And I'm going to show you how we can write some commands. So the steering files is divided already into some sections. All of this is optional because OpenTelemac is not going to read any line starting with a slash. So this is just for presentation and format. In the file section, we're going to put all of the files OpenTelemac should read. The time parameters and I/O is going to contain most of the simulation properties, like time steps and printing. The initial and boundary conditions is rather self-explanatory. This one is going to contain all of the physical parameters, and this one all of the parameters related to the solver. Let's start by the file section. In this section, we'll have to first put the geometry file and boundary conditions file. The steering file is simply a dictionary where you're going to put keywords, and if Telemac recognizes a keyword, he's going to try and read it. So, in order to say to Telemac that the mesh we're going to use is evet.slf, we just have to put the keyword geometry file equal, and here we are going to put the name of the .slf file. Don't mind the space, they are going to be skipped when OpenTelemac is going to read the steering files. Similarly, to specify which is the boundary condition file, we are simply going to write boundary condition files equal, and the name of the .cli file, which was createBoundary.cli. Another mandatory file we have to specify in the steering file is the results file. This is simply the name of the file that is going to contain all of the informations after the simulation. As a convention, the geometries file is mostly starting with geo. The steering file, when it's Telemac 2D, is conventionally named T2D underscore and then the name of your study. For the results file, in the same fashion, we are going to call it R2D underscore and then the name of the study for results 2D. Now, there are other types of files we can give to OpenTelemac for a given study. For instance, we could put the Fortran files. These files will contain additional Fortran code if we want to make extra operations. In this video, we are not going to put any Fortran file, so we can comment this line. Telemac will not read it. Let's move to time parameters and I/O for now. A mandatory keyword to put in this section is the time step. This is the parameter that's going to tell OpenTelemac what is the elementary time step of the simulation. Usually, if it's smaller, it will be more precise. But if it's really too small, it's also not going to work well for the convergence. You can find in the description of this video a document to help you to compute the time step accurately for the simulations you're doing. We also have to put a duration, which is how many time steps before the simulation ends. Here in the duration, I'm going to put, let's say, 20,000 time steps. Then, if we want to have something to extract from this simulation, we need to specify which are the variables we are going to track. Variable for graphic printouts is what's going to be saved in the results file. Let's put it here. Here we are not going to put a name or integer, but rather the name of the variables. So let's put with a comma all of the variables we are interested in. U is for the x velocity, V is for the y velocity, B is for the bottom, W is for the water depth, F is for the free surface, and Q is for the flow rate. Let's start with these ones. At any point, if you want to see what are all of the keywords, the reference manual is going to list all of the keywords that you should put in a Telemac steering file and give you the value we can take and what this is about. Note also that all of the keywords have a French equivalent, but the steering file should be written only just in French or just in English. If I'm going in variables for graphic printouts, you can see the name of all of the variables and what they represent that you need to put. I made a mistake. You see, W was not for water depth, it was for friction coefficient. Water depth is H. So now, we are going to keep the W for having the friction coefficient, but we are also going to insert H to have the water depth. Once you specified which variable you want for graphic printouts, you should also add what is the period of graphic printout that you want. I'm going to set it to 200, meaning that every 200 time step, I'm going to save the following variable in the results file. Finally, we can also add another type of period, which is the listing for printout period. We're also going to set it to 200, and this one is going to be the period for putting logs in the terminal. You're going to see when we will launch the Telemac simulation. Now for the initial and boundary condition section, we are going to impose the flow rate and water elevation profiles at the boundaries. An important note here is that every boundaries have a number. The numerotation of the boundaries can be found directly in the .cli file. The 222 in front of every line means that this is a solid boundary. This is a wall. Then, if we go down, we are going to see a 455, which is a prescribed flow rate. So this is the upstream of the river boundary we created on QGIS. If we are now looking for a 544, this is a prescribed water elevation, and therefore this corresponds to the downstream of the river we created in QGIS. So, since the prescribed water elevations comes first in the boundary condition files, this means that the first boundary is the downstream, the prescribed water elevation, and the second boundary is going to be the prescribed flow rate, the upstream of the river. There is already a script to not have to look in the boundary condition file that you can find directly in the Docker container. Indeed, if you go inside the OpenTelemac Docker container by typing the alias, and then you're going into /opt OpenTelemac script Python, here you have a lot of scripts, including a plot.py script. We can use the -h to see the help. Here we have several options, but we are interested into the mesh2d, which is for plotting a 2D mesh and add boundaries or liquid boundaries info. So let's do plot.py mesh2d -h now. And here you see that you have an option --- boundary, adding number of liquid boundary for each boundary node. Feel free to use this plot.py script in the case where you have multiple liquid boundaries with prescribed flow rate or prescribed water depth. This will allow you to distinguish them and know on which boundary you want to impose what type of value. Now that we know the number of our boundaries, let's prescribe some boundary condition. Starting with the flow rates, we know that the prescribed flow rate boundary is the second boundary. So in the steering file, we are going to write prescribed flow rates equal 0, semicolon 2. The semicolon is going to separate the different liquid boundaries. Similarly, for the downstream of the river, we are going to prescribe an elevation. To check the value of the water elevation to prescribe at the boundary, we can go on QGIS and look at the bottom variable. Let's click on our mesh and go on this button. Let's zoom very close to the downstream boundary and click some nodes. Here we see the bottom is 58. We have digged the riverbed of 2 meters. So this means we can safely prescribe an elevation of 60.5 to have about 1.8 meters of water at the boundary. Therefore, we write prescribed elevation equal 60.5, semicolon, 0. Note that if I put a non-zero value at a wrong boundary, for instance if I try to prescribe an elevation to the flow rate boundary, the value will just be ignored. Finally, we are going to impose some velocity profile using this keyword. If we look to the documentation, the velocity profile is a way of specifying the type of velocity in a boundary. We are going to impose a square root profile, so with the 4 on both boundary. This way, we have more velocity at the middle of the boundary than at the edges, in a square root type of manner. Therefore, we write velocity profiles equal 4, 4. And we are done for the initial and boundary condition. In the physical parameters, we are going to impose a law of bottom friction. Again, if we look at the documentation, there are several types of law of bottom frictions. Here, we are going to impose a Strickler formula, which is the most standard one for river flooding. So let's put law of bottom friction equal to 3. Even though we have defined the Strickler coefficients everywhere locally using the Corrinland cover datas in QGIS in the geometry, we still need to put a friction coefficient in the steering file in case it cannot read these datas. But this value is going to be overwritten by the one in the geometry file. So let's write friction coefficients and let's say 35. We could put much more in this physical parameter section, such as turbulence model, evaporations, rain. But for this first tutorial, we're just going to keep it simple and stop there. Finally, we're gonna write the numerical parameter section, and this one is the most technical because there are options to really change the solvers, so I'm simply going to put the following. All of these keywords are kept to their default value. The scheme for advection of velocities is basically a way of saying to OpenTelemac how it should compute the velocity field advection, propagation. The solver keyword is a way to tell Telemac how it should make this computation numerically, using which method. Solver accuracy is usually set to 10 to the minus 4, and we are not going to change it. And the mass balance keyword is to have a computation and a log printout of the inflow and outflow in the domain at every time step. Please refer to the reference documentation if you want to see the different values for all of these keywords, and don't forget to look at the user documentation if you want to understand the meaning of these values. Finally, let me show how we can execute the steering file and run the simulation, and I'll cover the topic more in detail in the next video. You can open a terminal. In my case, I'm going to open it directly in VS Code and run the Docker container. Then go to the folder where you have the steering file, and then go in /opt, OpenTelemac, scripts, Python, and telemac2d.py, and put the name of the steering file. And Telemac will start running. Here you will notice we have a few mistakes. This is just to show how we can debug a little bit the program. So you see the first error is because it doesn't know the word variable for graphic printout, and this is because it's variables. This second error is usually caused either because the time step is too big or because you have dry liquid boundaries and it crashes. In order to solve this issue, I'm going to show you how to make a Telemac hotstart. To do that, let's just put computation continued equal yes and previous computation file equal to the name of the geometry file. This way, when Telemac will read the file, it will also extract the water depth. If you do not put this keyword and just use a geometry file, OpenTelemac will just ignore the water depth field and consider that the boundaries are dry. Thank you for watching this video. In the next video, I'm going to end this tutorial by showing how to make some post-process in Salome using Paravis, and also give you some additional trick on the steering files. In the meantime, feel free to subscribe and stay tuned for the final part of this tutorial. Goodbye!